It is visible to you, right? So I think you have all this document with you. So
Yes.
okay. So experiment 6 we are going to do today in online. So in online we cannot do all this experiment. So what we'll do, we'll discuss about the theories, the instrument, and then we'll discuss the procedure how we can do actually in the lab. So the title of the experiment is Studies on Spectral Composition and CCT of Different Labs. Okay. So I have prepared one PPT for you all so that we can understand more easily. Just a moment. Just switching off my videos. Um, are you able to see my screen, right? Hello? Are you able to see my
Yes, ma'am.
screen?
Yes,
Yes,
ma'am.
ma'am, it is visible.
Okay. So this is the title. So in objective, what was the objective of this means lab? The objective was to observe optical structure of different type of lamps and incandescent, CFL, HRD, etc. Different kind of lamps physical structure we had to observe, but without the actual lab this is not possible. So we'll do the later part, the study of the spectral composition of different lamps with constant deviation spectrometer. So here the instrument is used for spectral composition of different lamp, that is the constant deviation spectrometer. So what is a spectral composition? Anyone can say anything about the spectral composition? Spectral composition is basically the spectral power, means optical power, which is associated with each wavelength in the spectrum range. We know about different wavelength or spectrum, right? So in each wavelength, what is the power, the radiated power, optical power it is giving by a lamp, that is the spectral composition. Here we are going to means by experiment we want to know. So here the instrument is used is constant deviation spectrometer, and another one we are here to measure to correlated color temperature. Okay, correlated color temperature, or the we call it in short CCT of different lamp, and for that purpose we are going to use the chromometer, another instrument which is a chromometer. Okay, so CCT, what is CCT actually? It is actually the it is not the temperature of the lamp. It is the temperature of a black body. When the black body, if we drive means heat the black body in that temperature, the appearance of the black body will be similar when you drive the lamp in a rated power or rated current voltage, like rated wattage. Then the appearance of the lamp will be look similar to the means black body when the black body will be heated in that temperature. So this is the CCT, the correlated color temperature. And next one is, then we have to relate or establish a relation between the CCT and the spectral power composition of the different lamps. So with this three section I have already told, we are going to follow. So in our lab we will be using, if you could have been there, so we use mostly the incandescent lamp, or in normally called is bulb, or the GLS lamp. This is the appearance when it is glow, when it is driven by a rated power. So low pressure sodium vapor lamp, that is a SOX lamp, and this is the appearance. It shows the appearance. And then cool white compact fluorescent lamp, this is the compact fluorescent lamp, and it is a cool white. Why it is cool white? Cool does not mean it is the cold things, because the appearance, if you see this light when it is glowing, it resemble to the ice. When there is ice, and ice is like cool or cold kind of thing, so the name came from the there. Actually it is called the cool white, or we called it CWCFL. Okay, warm white, if you see this, you will see the yellowish part is more, and in the light looks like more yellowish, and as the fire color is little bit kind of a yellowish, so we say it is a warm white or CFL. So this appearance comes due to the different spectral compositions, and due to that spectral composition, the CCT value will be different. And here if you see for CFL warm white, you will see the red component or yellow component is more. If you see for white means cool white CFL, then you will see that the blue component is more. Like that we can understand from the spectral composition of different lamp. So this is the 4 lamp we will be using here. So this is the spectrum or emitted radiation. So you can see that there is ultraviolet radiation from the smaller wavelength to around 400 or 380 nanometer, we called it the ultraviolet. And this is the visible radiation. We know that 380 to around 380 780, or we call it 800. If we approximate 400 to 800 nanometer is the visible radiation, and higher infrared above 800 nanometer. So here for this we all know about the prism, and how the prism dispersion of the prism. Then it breaks the white light into 7 different spectrum. So this is the principle we will use here in that. Actually these principles is used here in our constant deviation spectrometer. So spectral composition. So different source actually produce different distribution of radiated power throughout the electromagnetic spectrum. So if you see there is the lines of different wavelengths. So wavelength actually representing different colors. So color and wavelengths is like you can use it like the red color, or you can just say it is mark it as a wavelength. So through in different visual sensation it creates, and we appear is like different color for different wavelength in visible range only. So um, the spectral composition for lamp, there is a two-way representation. One is one dimensional and another one is a two-dimensional presentation. In one-dimensional presentation, you will see the wavelength information is only given. You will see different wavelength, and you will see what is the light is coming out. This dark region actually representing that there is no power radiated in that region. So no power is radiated. So this is the similar one, means one dimensional representation. You can see there is only the line spectrum, and this is a continuous spectrum, means you cannot differentiate one color from the another color. So this is a continuous spectrum, and this is a line spectrum. For different lamp they will give like continuous spectrum or the line spectrum. So this is the another way of the line spectrum. This this is the two-dimensional presentation of spectral power distribution plot, where you will get the information of the wavelength and as well as the power, spectral power distribution, means how much power it is radiating, and each wavelength you will get the value. So there is another instrument called spectroradiometer. You can from the name only you can understand that it is measuring the power, the spectral power at each wavelength. So but here we are not going to do that experiment. So here we will only get the one dimensional presentation. So this plot is called actually SPD, or spectral power distribution curve or plot. So if there is a thermal radiator, it gives the SPD curve is continuous. If there is a gas discharge lamp and some other lamp, it gives the line spectrum. So it actually provides the information how much portion is visible and total amount of the radiation, and it calls the SPD. So if you see, different, this is taken from the internet, because we are not means doing the experiment with this kind of lamps, but just to give you an view that what kind of distribution shows by different lamp spectral distribution. So this is for a tungsten incandescent lamp. You can see this is a continuous spectrum it is giving, different color, all the color is present for daylight also, as it you can see the wavelengths, and also the radiation is for each wavelength is high, and it is continuous. This is a mercury fluorescent lamp, different line spectrum in different color wavelength it is actually radiating, not in all the wavelength it is radiating. We all know that a SOX or low pressure sodium vapor is a monochromatic in nature. That means it radiates a single wavelength, but it is not actually the means radiates in single wavelengths. There will be little bit or faded radiation in different other radiation also, but this wavelength at 589 or 9.62 wavelengths are very prominent. The radiation is very prominent, so that's why we call it the low pressure sodium vapor or SOX lamp. So this the distribution of a high pressure sodium vapor. This is for metal halide, and this distribution is for cool white LED and warm white LED. So cool, you can see from the cool, the blue portion is more, and warm white, the red and yellow portion is high. So that's why it is looks like more yellowish, and the cool white LED it will look like more bluish. So another one is the next parameter. What we are going to measure is correlated color temperature, and as I have already mentioned that this is the temperature of a black body whose color appearance is most likely or nearly resemble that of the light source. When light source is glowing, how does it looks? So so you can see if the color temperature is more, it will be more whitish or more bluish. Okay, so this can be explained easily from the Wien's displacement law. You know the peak radiation wavelength into T equal to constant. So you can say the peak wavelength radiation occur is inversely proportional with the color temperature or the temperature T from the black body equation. You can say, so if the black body temperature increases, the peak radiation will shift to the lower lambda, so that's why it will be nearer to the blue or more bluish. Now this is just to show when you have means light up some room with different lamp, how does the appearance will be like. In daylight it will be very white and clear, in cool light it is little bit means white is bluish, and in warm white it is yellowish. So the temperature is if it is less than 3200 Kelvin, the color temperature we may it will be mostly in the red side spectrum, and we call it the warm. If it is greater than 400 Kelvin, so we call it the cool or the blue side of the spectrum, and daylight temperature is 500 K around. So up to this is the theory part. So up to this, do you have any question? We will go to the instrument then. Okay. So we'll move to the instrument. So what we are using here is a constant deviation spectrometer. You can see this is a constant deviation spectrometer. It is there in our lab. Nowadays this kind of instrument is not actually available in the market. There is different kind of digital instrument they use, and this is the chromometer. Okay, are you able to hear me right? If any problem, please let me know. Okay, CCT range is 2000 to 10,000 Kelvin, and here wavelength for constant deviation spectrometer we can measure from 360 to 800 nanometer. Just to confirm that you are able to hear me or not. Uh, are you able to hear me right?
Yes, ma'am.
Okay. So if you see the constant deviation spectrometer, the construction, so it has this different part. Okay, it has one collimator here and here one telescope here. So light will come from here. There is one prism here. So prism, due to the dispersion, it will be in different spectrum. It will be means it will be in different spectrum. Then we can see through the telescope. So how you can differentiate between a collimator and the telescope? You will see there is a eyepiece here. Here one eyepiece will be there. From there you can understand which one is the telescope and which one is the collimator. So collimator, what is the purpose of the collimator? It converts the diverging light rays into parallel beam of light. Then it will fall into the prism. Different wavelength will fall into the prism, and prism will split the incident parallel beam of light into constitute wavelength, creating spectrum of incident light. So it will create the spectrum. Then the telescope, it will convert the parallel beam into converging light rays, and we will be able to see it. This is the actual setup in our laboratory. You can see here, this is the SOX lamp. For this experiment, first we have to actually calibrate the instrument, and for this calibrate purpose, as we know, the D line or the monochromatic radiation for a SOX is 580.6 nanometer. So this instrument, we have to calibrate it with that SOX lamp first. So we'll light up the SOX lamp. Then here is a drum. You can, I don't know, behind this there is a drum. You can rotate the drum so that the prism will rotate, and it will change the incident angle of the light. And here is one slit. This slit actually will from where you can increase or decrease the slit so that the falling incident ray will be thick or thin, like that it will be. And here one magnifying glass is there, from where the wavelength which is written in the drum scale you will be able to see. And here the eyepiece is here. So in the eyepiece, actually there will be one wire like this. So there will be one wire like this, and if the spectral comes, we have to coincide the spectral lines with this line, so that it gives the measurement or drum. That time the value of the drum which it shows is the wavelength value for this means line, or that is will be the wavelength for this green, blue, white, whatever will adjust, coincide with the where you can coincide in the right side or the left side. Mostly what we'll do, we'll means rotate the drum in means like we'll move all the spectrum in right hand side or all the spectrum in left hand side, and then we will start doing rotating the drum, and one by one we will check what is the wavelength of different lights, different spectrum. Okay, so if you open this, you can see this, there is the prism. The prism is named as this is a special kind of prism. It doesn't this is the look of the prism. It is a special kind, because why it is called constant deviation, I'll say it. This prism is actually looks like that, and you can see the incident line through the collimator it is coming, and the prism mechanism is made in such a way so that the emitted light and between the incident light, this angle will be always at 90 degree. If it is not in 90 degree, this will not come through the telescope and you won't be able to see it. So what we are doing, we are adjusting the incident angle here, and we are getting the emitted light at 90 degree. At this angle is all the time fixed. That's why it is called a constant deviation spectrometer. And there are different other spectrometer also. There we have to actually move to see this light. Depending on the incident, we can move the telescope, so that we have to find where the light is coming out, from where the light is coming out. But for this is a special purpose, and this is fixed. So so emitted light and incident light, the angle will be always at 90 degree. That's why it is called the constant deviation spectrometer. So when we are actually rotating the drum, this prism is actually rotating through the mechanical arrangement. Here is the drum, you can see a small portion, it is here, it is visible. So it is moving, and then the incident angle is getting changed, and the emitted angle or different wavelength we can see through the telescope. So this is the another instrument, chromometer, CL200A, what we use here. This is made by Konica Minolta, and range already I have mentioned. For K it is 2000 K to 10,000 K almost. So this is the mirror. I'm not going to the detail. So as you know, the light is the visual response to human eye, the perception of human eye. So it varies with the human. So different person will have different visual sensation or visual response. So there is actually standard which has given by CIE, so that studying different visual response of different around 52 person, they have done the experiment, and then they have given a standard curve of visual response, relative spectral response curve we say, or for a photopic vision, the peak will be at 555 nanometer. So when the light radiated in this region, so we will able to visualize more comfortably or clearly. If the light in other region, the response, as the response of our eye will be less, so we will it will not be so means responsive, or our light will not be response of our eye will not be good. So when we are using a sensor, so that is a physical way of measurement. So we need a sensor where we'll use some LDR or some photodiode, so where to sense the light. So that time the curve of that means this kind of curve or this filter will have to put on that diode or photodiode, so that the response, visual response, matches with the human eyes. This is the cosine correction characteristics. We are not going into the details. This is also needed for any sensor, because of the the intensity varies, means illuminance means I equal to I theta means with the cos theta, it varies, the intensity actually varies. That's why if it is the light is coming in different direction, the intensity will also change or vary with the cos theta curve. So that's why we need some filter also for cos theta correction or cosine correction. This is the specification. So in our lab, the lamp, we will be using this lamp. Here the actual measurement in from I means picture from our lab. So we'll use, this is the GLS lab, a lamp 60 watt, 230 volt. This is the SOX lamp. We'll use 35 watt SOX lamp, and you can see 2 CFL of different color temperature. One is around 2700K to 3000K, and another one is 6500K. We'll use in our lamp. So what is the procedure? First we have to calibrate. So how we can calibrate? So mm, let me go. So we have to calibrate means we have to calculate the error. So we know, I have already told that the SOX is in monochromatic in nature. So it is yellow radiation is 589.6 nanometer. So if you see the instrument, oh, sorry, if you see this instrument, so first at the starting we have to calculate the error. So we have to light up this SOX lamp, and then we have to rotate this drum. Here is the drum, there is a knob, you can rotate it, and we have to put our eye in this telescope hole or there, and then we have to see the wavelength or yellow wavelength which is coming through this telescope. And we have to check, there will be one point in the drum which is marked as cross as 589.6. So it is falling on that or not, we have to check. If it does not fall on that, so that means there is a error, so we have to estimate the error using this formula. So like if the error is more less, it can be less or more, so it will be depending on that, it will be positive error or the negative error. What is happening? So after the error or calibration is done, then we will use the other different type of lamp, and we will place here, and we will check the spectrum, and we will note down the wavelength seeing from this magnifying glass. Okay, so this is one kind of real measurement. Here you can see the SOX is powered up, and then it is checking the wavelength in experimentation. And for the SOX, you can see the yellow line, you can see it is very prominent, and it will there are some others color wavelength also is present. You can see from the line, it is a line spectrum, mostly monochromatic, not means so this is a chromometer. So you have to put when the light is for this experiment, we have to use a dark room, and when the light is on, this lamp or light is on, when the experiment is going on, you have to switch off the other light of the laboratory, and then you have to take the measurement, and you have to take the result. Then you have to place I think for chromometer or the CCT read measurement, you have to just put the chromometer. This is a digital instrument, so you can understand, you can easily get the value in a display. So but for this instrument, you have to first do the means calibrate the instrument or error zero correction we say. So what we have to do, you can see a cap here, this cap we have to put here. So in the instrument, there is inside there is some measurement or circuit is there. They will, if they shows the 00, if you hold for 5 to 6 seconds or 1 minute, then the instrument will automatically calibrate, and it will show the 00 reading in the screen. Then we have to start the measurement. And after doing this zero correction or zero error correction, so you cannot put the cap on. If you cap on, and then again we have to do the zero correction. So like the way you can see the CCT value it is showing when you are putting. So this is the easy part. And okay, so this is the experimental setup, and this is the line spectrum for low pressure sodium vapor or SOx. This incandescent lamp is a constant ionization spectrum. You will be able to see when you could have been there, you will be very excited to seeing this kind of light is coming. So it will be continuously the light is coming for cool white and warm white. You can see this is for the warm white, the red portion is much more, and there is some gap, but it is not actually the line spectrum. You can see there is a range of wavelength for a particular color. So there will be range, we cannot differentiate, because for this is a lamp where we are using the phosphor. How the light is generated from a fluorescent lamp? First, due to the discharge, the discharge will emit the light in the UV region. Then we will will be some phosphor coating inside, and this phosphor will excited and convert the UV light into the visible light. Due to the phosphorus coating, actually this means mixed kind of spectrum we are getting from the CFL lamp. So for cool white, the blue region will be more. So after the experiment, so this is the way we have to present the result. Means for first for SOx, we have to take the measurement, then other, and what is the spectrum we are saying, we have to write the means the wavelength in nanometer, and then we have to measure the CCT and also write it down. If we cannot means for CFL and warm white, we cannot actually point out the exact wavelength, so we have to write the range of the wavelength. So this is a sample item. You can see this is the instrument we have used in our lab, and one result it is showing. See, so it the measurement will vary different when there will be different group, the different group they will get different result because due to their visual response. So you can see measured zero error. Here they have measured error is as a 0, and for sodium vapor, not only see 589.6 they have got the yellow which was very prominent, but for other means other color also they have got some other spectral line also for different color like red, green, blue, orange also they have got. Very faint maybe, but they have got. It depends on the visual property of the person who is seeing. For warm white, you can see this is a mixed spectrum, is a mixed, it not the line spectrum and not the continuous, it is a mixed. Somewhere there will be no power, means it will be black, no power radiation, then it will be a continuous for some color band, and then again there will be black, and then I have shown the spectrum. So that's why for different color they have written the wavelength range. And from in a wavelength you might see some line is very prominent, so they have seen some spike here also. You can see 629 they have seen a very prominent bright red light spike as a spike. So who have done this experiment, they have seen these spikes for different color, as they have seen a continuous faded light and also a spike. So that's why it is called a warm white or means mixed type spectrum. And this is the experiment for cool white also. They have seen. So, and for incandescent lamp, so it is a continuous, means there will be no black portion or no black portion of the spectrum. And for the CCT measurement, or CCT measurement of the lamp, so you can see the low pressure sodium vapor lamp. The low pressure sodium vapor lamp is CCT is actually below 2000 Kelvin, so they could not get the value by the chromometer, because the chromometer's value source from 2000 Kelvin into 10,000 Kelvin, so it is beyond chromometer's range. So that's why they could not actually, the for socks it will be around 800 1800 Kelvin. So that's why they could not get it, and that's why they have written it less than 2000 K, and it is beyond chromometer's range. And for other lamp, incandescent lamp, they have got like 2556. You can see this is near to the 3000 Kelvin, and if you light up the incandescent lamp or ball, it looks like yellowish. And warm white, it is around again around 3000 Kelvin near. And for cool white CFL lamp, they got the CCT value is higher range, 5000 above. So now, if there is any question. So last part was the correlation. I think I have already correlated the CCT and spectral values. Means if the CCT is less, that means the color temperature is less. So it will be in the wavelength will be more in the red region. So it will be like more warm white or yellowish in nature. If the color temperature is high, it will be in the bluish region. Blue content will be more, so it will be in the bluish region, the spectral power distribution or spectral power radiation, and it will looks like bluish white. So from the spectral power distribution, you can understand, and also from the CCT you can understand in which color of light or which wavelength the means region the means lamp is going to radiate their power. Or this is the total procedure and the experimental things. So let me stop present and come back to you. Himadri does it not came, right? Himadri, hello, are you all there?
Yes, ma'am.
Yes,
Okay.
ma'am.
So any queries, or it is clear the lab how we actually do in our laboratory? And I know you all are missing the lab, but is it clear to all? Okay. I Nobody is answering anything, so we can say if you are silent, that means yes or no. I try to explain the things. I don't know.
Ma'am, how will we write our lab report?
Lab report. Okay. So you're concerned about our lab report. See, in this lab, actually, you can see that what we are doing. Means in most of the lab, you go and you get some result, and after that, you have to do some calculation, and then you have to plot something like that. You have some other work to do after getting the data. But for this lab, actually, you can directly see that there is no work after getting the measurement. So the report is like the values of nanometer, whatever you are getting, means nothing else you have to do after the experiment. You have to just arrange the things in a proper way, the way the lab report we make, and then we have to submit. Means there is no other things to do after the measurement. So
Okay,
what we have
ma'am, you have seen, you have shown in the lab report up to the measurement of CCT. So our work is to done up to that actually, and there are some sample questions. Should we have to answer them?
Yes, I'm coming to that. So if you see one lab report here, this is someone old pass out. Okay, so if you see the lab report, so you know how to write a lab report. So this portion, somebody draw some means constant deviation spectrometer picture also here. Sometimes it depend on the student. This is the apparatus list.
Ma'am, you're not sharing.
Oh, sorry. Sorry. You can see I have one old lab report. So you know how to make the lab report. So this has been done by SDC sir. He was the concerned teacher, and somebody also draw some some means constant spectroradiometer, the picture here and all those things. That is depends completely on the student. So this is the two part which already nothing to do. Then the apparatus list. This is the things you have to know, or the information you have to get from me, right? Because you are not in the lab, so you cannot see what is there. So this is the page you needed for to make a lab report. And then the observation, this observation should be done by the student, but here we are giving you the old data because the situation is not permitting us to do the experiment. So this is the data. This page also you need. So you can see this is the page, and after that there is a measurement of CCT, and this is the data which we are measuring in the lab. So after that you don't have to do anything for this experiment. What, that's why there is some questions given in the lab sheet to answer. And actually we do not answer when actual lab is actually going on, but due to these online classes we have decided that with the report, as you are not doing yourself anything, so we'll short out some sample question along with this means I'll send the data along with some question. You have to write the question in your own way, and you have to just prepare the report. And I think 1 week is the time for you all, right? So within 1 week, not from today, the day you will get my mail regarding the data and the question, sample question, the question which is there in the lab report, it may not be the same thing. We'll discussing with our senior, and so then I will send the data and the question, sample question which we have to write, and you will prepare the lab sheet and you will send through mail within 1 week, right? So no confusion, right?
Yes, ma'am.
Okay. So I think the lab was actually interesting, very interesting, but you are actually missing the lab. We are also missing you all. Doing the things by hand is gives different experience, and something is which you are going to miss, but what to do. So I think there is no more question, but Himadri is not joined. So should I do him absent? He will be absent, and again I have to tell him. Himadri, okay. Himadri Das. He is the person who is only absent. I don't know it is for my fault or not. If it is for my fault, then I have to do something. তোমরা কি একটু হিমাদ্রিকে বলবে আমাকে ফোন করতে? ওকে, আমার ফোন নাম্বার মনিকার কাছে আছে, বাট আই ক্যান শেয়ার ইন।
আচ্ছা ম্যাম, ঠিক আছে, আমি বলে
ওকে,
দেবো।
হ্যাঁ একটু বলে দিও না ওকে যে আমাকে ফোন করতে জানাতে কেন আসতে পারলো না বা কি হলো। ওকে ওকে, তাহলে আজকে যদি আর কোনো মানে কোয়ারিজ না থাকে তোমাদের, তাহলে তো আই হ্যাভ টু এন্ড দ্য মিটিং। তাহলে কি এটা এন্ড করব? ল্যাব নিয়ে কোনো কনফিউশন নেই তো? মানে যেদিনকে ল্যাব রিপোর্ট পাঠাবো from that day, I will count 7 days. Within the 7 days, I am expecting to get back the report. So I think so. So I am ending up the meeting here.